Stephen Gagel, you're not, are you here? Okay. Okay, a few more students. Is there anybody here that had a birthday over the weekend or today? It's your birthday? Today's your birthday? Anybody else? Let's sing happy birthday. Happy birthday to you. Happy birthday to you. Happy birthday. Come on, you guys. Happy birthday to both of you. Excellent. Yay. I just felt like doing something fun. Okay, Angelica's here. We're ready to go now. No messing around. A couple things I want to mention to you. A week from today is exam number 2. And oh my goodness, we've got a lot of stuff to remember for exam 2. It's going to be full of stuff. So for instance, stopping time, stopping distance, you know, the impulse formula and the work formula. You're going to want to know how to do that. By the way, I saw a student this morning came up before class and showed me, are you Stephen? Okay. See, he looks a little bit like Stephen. Stephen Gagel. Are you here yet, Stephen? Okay. It's one of the students worked out all the different rows of that freefall table that was on Talking PDF. And she brought it up here, and we were just looking at the patterns and stuff. So I highly recommend that for you as a study tool to get ready for exam number 2. You'll be happy that you spent some time on that. Now, last time we discussed angular momentum. And I like this photograph because it shows that this ice skater is spinning. I mean, it's a photograph, so you can't really see the motion, but this ice skater's skirt is going straight out. So that means that only happens when she's spinning. So she's probably spinning plus her hair. If you look at her hair, it's kind of flying out in the universe as well. So that's pretty good. Now, angular momentum, as I mentioned last time, you can think of as the momentum of the ice skater. And it's the quantity that is conserved when the ice skater is spinning. You know, they develop a certain amount of angular momentum, and then they redistribute the mass in their body. You know, they extend their leg or they extend their arms or something, and they spin up and spin down. Now, it leads us to this question: what is it that can change the angular momentum state of a skateboarder? And we're going to talk about that today. Basically, the answer is leverage and torque. So here's an image from page 64 of the hardcover or the ebook version instead of the website. A couple pictures of shrimpy little kids. But before we get to You didn't bring one for everybody?
Oh, no, they're just making it.
What is it, Free Smoothies Day? Over at Smoothie King?
No.
Oh, okay. Whew. Okay, so you guys, that fifth row over there, it's the smoothies row. Let's do some clicker items. Warm up with some clicker questions. Go ahead and we'll try to soldier on without a smoothie. Good gravy. I don't know about you guys sometimes. But I'm glad to see you. right, so get your clicker ready. Now, here's a diagram I want you to think carefully about. So this is multiple choice, A, B, C. The black dot is 40 kilograms, the white one is 50. They're same distance, 2 meters from the fulcrum, the pivot point. So how does it spin? Go ahead and vote. Stephen Cagle, did you just walk in? Gagle. Stephen, Gagle. All right. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pretty good. Let me see what you guys voted for. Yeah, the correct answer is clockwise. And let me grade that. Good. Now, slightly different. How does this one spin? Look at it very carefully. Clockwise, counterclockwise, or no spin? Ten seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pretty good. You guys did well. This one is balanced, so it's not going to spin. Until you redistribute the weight or put some additional weight on one end or something like that. This one's going to be balanced, and that's kind of what we're talking about here. And recall that this diagram here at equal positions, my son defeats his little sister because he is heavier. That's from the textbook. And what we would say in the physics department, in addition to the conversational sentence at the top, we would say that the sun at point L creates more torque about point P. So we're going to talk about torque and leverage today. And it starts with the context of a seesaw, but it extends, to, gravitational orbits of planets and stuff. It's pretty important. So the torque you develop depends on your position, where you are on the seesaw, for instance. Are you in close at 2 meters, even Steven? Or are you out a little bit further so that you can balance your big brother? Also, how many newtons that you push or pull, how many newtons of weight force are you exerting downward on your end of the seesaw? Okay, so that depends on your weight. And as I mentioned here, this is from readings in chapter 5. Now, this diagram here, also from chapter 5, shows you what we mean by the direction and the location at which you apply a given force. All right, so if F1 is applied perpendicular to the door and the hinge being out, let me get my cursor up here. Come on, baby. Okay, so here's the hinge over here, right? And that's kind of like this door over here on the left side of the stage. Okay, the hinge is on the right side. All right, so F1 is pressing at the edge of the door, and it's pressing straight in, perpendicular to the door itself. So that's like on the hand plate over there on the left side of the door. Now F2 down here, This guy's, he could be applying the same amount of force, but the door's not going to open. It's not going to swing anyways. All right? It's not going to move anywhere because he's pointing directly toward the hinge. Now, if this door were free to move, he could get the door moving to the right with that force, but he could not get it to spin. Same thing with this, the one on top. If he were, are you Stephen?
Yes, sir.
Stephen Gagel?
Yes, sir.
Okay, good. You're late. Okay. So this one up here, you could put some newtons of force on it. You would get it moving, accelerating upward, and it would spin because it exerts a torque about either the hinge axis or the natural axis, the center of mass, which would be the center of the door. Okay, so this is maximum torque, and this is zero torque down here. So make a sketch of that. And that'll be good. All right. Here's a set of vocabulary terms that I want you to also make a note of. Translational and rotational. If you put a force on the center of mass of an object, so like for a door, something like a door, it's fairly uniform materials, it's going to be pretty much the center. Your center of mass is right about your belly button. So if somebody gives you if you're out in space and a space alien gives you a sock right in the belly button, right in your solar plexus, you're going to go flying off, but you probably won't spin unless he gives you a roundhouse kick on the way out, just like Chuck Norris. Now, if you get a torque, you're going to develop some rotational motion. And it's possible to also have a combination of both. And this diagram shows an object moving along a parabolic arc, and also spinning a little bit. So now here's an example of that, if you think about it. If you watch a guy playing football and they try to kick a field goal, the ball goes end over end. So the ball is spinning and it's also following a parabolic arc at the same time, and hopefully they get the field goal. And versus the punter or the quarterback, they put a spin on the ball. So actually it is the same thing. They put a spin on the ball so it's not going end over end. It's spinning about the long axis, and that helps it travel a little bit further instead of end over. End over end, you can get more force on it. Spinning it gives you a little bit more accuracy. It'll be on the money where you want it. Okay, so the rotational analog of force is called the torque. All right, and we know that the net force changes the regular momentum state, delta P over delta T. All right, so that's squared away. And so the question is, what is it that the torque changes? Well, a frequent symbol that you'll see for torque is lowercase Greek letter tau, which is what I've got here, Connor. All right. And sometimes you see, what do you see? Greek letter gamma sometimes. There's a variety of symbols, but I'm going to try to state a lowercase Greek letter tau. Has an arrow over the top of it. And it's delta something over delta t. Now, the something on the numerator of that formula for torque, tau, is angular momentum. So angular momentum also has a vector structure. It's a vector. So, but the thing is, it's the momentum of spinning. So you can't say that the angular momentum is going to take you to Albuquerque or from point A to point B. All you can do is tell me, is it clockwise or counterclockwise from my point of view? All right? But there's a way to give that a vector direction, and we'll do that at the end of class probably, hopefully. And if not, we'll do it first thing on Thursday. There's two kinds of angular momentum. Okay, the first one is called orbital angular momentum. So something that's on a curved path around a central point. All right, so like a planet orbiting the sun. An electron orbiting the nucleus of the atom. You know, for hydrogen, an electron orbiting a proton. That's a hydrogen atom. A comet. You know, an asteroid, anything that's orbiting the sun, is you definitely want to know the angular momentum state, because the angular momentum state, you know, how many kilogram meters squared per second of angular momentum you have, that determines something special about the orbit. The other kind of angular momentum that you have is the ice skater, the angular momentum of spinning. Now, if the ice skater is you know, the thing is, an ice skater can also have orbital angular momentum, because you've seen them. They go on the ice and they skate in a circle. You know, they might not be spinning, but you know, if they aim their ice skates properly, they'll go. You know, and they lean into the curve and stuff. They'll go around in a circle. So spin angular momentum, usually. The axis that we care about for spin angular momentum is the axis that goes through its center of mass. So, and there's some mysterious features. Let me pause the lecture for a minute here. I noticed an error with my next slide. Hold on. Let me get my cursor over here. Okay, so let's take a look at orbital angular momentum. And usually, when we're thinking about angular momentum, we have to define some point of interest around which the object is moving. So, like, for instance, the sun, and, you know, a planet going around the sun, like the Earth. So here's a picture. That green sphere in the middle represents the sun, and there's the Earth. And the Earth is going on a pretty circular orbit. It's slightly elliptical, but not by much. You'd be very hard put to distinguish Earth's orbit from a perfect circle. But there are other objects, you know, for instance, a comet. And we'll do an overhead view of a comet's orbit here in a minute. But, you know, comets frequently have more ellipticity, but they do have an angular momentum state, and it's relative to the SUN. Now, the distance and the angle from that point on the orbit to the sun, your central point, is part of how you determine the angular momentum. Because remember, the angular momentum, it's all about where the matter is. Is it moving in a spin? Is it moving in a curve? And where is it? How far is it from that central point? In this case, the SUN. But you know, it could be something like an electron, you know, around a nucleus. So we use the angular momentum. If you've had chemistry class, raise your hand if you've had chemistry at some point. Okay, a few of you. And you know, in chemistry class, they give you these weird-looking diagrams of atoms that look like balloons and barbells and stuff, and that's because of the angular momentum state of electrons. So all that stuff is important. You also have to have the velocity. You know, it's like an mv, but it's actually mv at a position r. So in this diagram of the Earth, I've got position R down there. Here's the velocity. Okay, go ahead and, if you're looking at the solar system from the North Star, from above, all the planets go counterclockwise, and that's what we got here. The Earth goes counterclockwise. We're a little bit north of the solar system, towards the North Star. So make that the velocity vector, and on a circular orbit, the angular momentum formula is pretty simple. Capital L, that's the symbol for angular momentum. And sometimes you see other symbols, like capital J, capital S for spin, angular momentum. But we'll use capital L. And it's just simply the mass of the object times its speed v times its distance r from the center of consideration, which in this case is the SUN. Right? Now, this vector r, the position vector r, and the velocity vector v, those are we have to construct a vector, an angular momentum vector, from those two. All right? So the angular momentum vector, you can make a note of it, it's not going to be in the direction of v, the way that regular momentum would be. It's not going to be in the direction of r. It's actually going to be perpendicular to both of them. If you think of the r and the v as forming a plane, like two, fingers or two pencils, and you could balance a sheet of paper or a sheet of cardboard on top of it, that plane of the cardboard, perpendicular to that plane, that's where the angular momentum vector is. So it's neither in the direction of v nor in the direction of r, but perpendicular to both. Now, let's take a look at an overhead view of an elliptical orbit. So go ahead and draw an ellipse, and you can see my proportions down below there to the lower right. The half the width is 400 pixels, half the height is 240. The sun is located 320 pixels to the right of the center, and the eccentricity is 0.8, which you don't have to worry too much about those, but that's the proportions. I did this real carefully. Now up here is the comet, so we'll just put the comet. It's blazing around its orbit. No special point. It's not like it's not like at aphelion or perihelion. Here's the sun down here. Sun is at the focus, the right-hand focus in this diagram of the ellipse. Every ellipse has two foci, one to the left, one to the right. And this what Johannes Kepler found in the 1600s was, about the same time as Galileo, that every planet has an elliptical orbit, and the sun is exactly at the center, or not the center. The sun is exactly at one of the foci of the ellipse. So that's how we draw this in here. And it's true for comets as well. Halley's comet that Edmund Halley figured out. Here's perihelion over here. The closest point of approach, here's aphelion out here. The far left, the point of furthest travel. Okay, so out here at aphelion, the comet would be just kind of poking along, kind of slow. And over here at perihelion, it's really whipping because it's closer, stronger gravity, more G's of acceleration. And out here at aphelion, just, it's kind of weak out there. So it's moving, it's on orbit, it'll come back, but it's taking its time. It's kind of slow and pokey out here. And the comet that I've got drawn here is just kind of somewhere in between, some intermediate point. Now, go ahead and draw a vector from the sun to the comet. All right, there's your position vector R. Okay, and trace in a velocity vector, okay, that's tangent to the red ellipse. So just like that. There's my velocity vector. All right, so this is an unusual comet. if we're looking at this from the North Star point of view again, this is a comet that's going clockwise, which there's a few. Most comets are going anti-clockwise, but a lot of them, there's a good number that go, some of them aren't even in the same plane as the planets, but a lot of them are. Anyway, so that one's, it's tangent to the red ellipse, the red elliptical path, and so there's an angle. So you can see there's an acute angle between those two babies. And they form a plane. You could bounce a piece of cardboard over the top of those two arrows. And the angular momentum vector would be up from that piece of cardboard. Now the thing about this is, on this diagram, you would need a lot of trig to figure out the angular momentum. So we're not going to worry about that. I want you to look at that picture and remember it, but don't worry about that angular momentum. Angular momentum is a walk in the park on circular orbits, because circular orbits, they're always the same distance away. So there's no perihelion, there's no aphelion, there's just the orbit, same distance each time. And the elliptical orbit, you get these, these angles and stuff, you got to use trig. But for a circular orbit, the vector r and the vector v they're always going to be perpendicular, right angles. So you just multiply them together. However many meters of distance, that's your r. How many meters per second of speed, that's your v. How many kilograms of mass you have, that's your m. And you just multiply them together. And that will give you the orbital angular momentum. And also, here's another thing you can think about. Here, this is kind of a side note. We're not going to really worry about it too much. But just a side note, on the ellipse, like this one, there are 2 points where the position vector r and the velocity vector v are perpendicular. And those 2 points are aphelion, furthest point, and perihelion. Okay? And so the r is smaller for perihelion, but the v is bigger. And the m is the same. The r is bigger for aphelion, but the v is smaller. Okay? And so the angular momentum of the comet is going to be the same everywhere on its orbit. It's a constant. It's a conserved quantity. And that's why if you know the speed at perihelion, you can figure out the speed at aphelion, because MRV is going to be the same. If you know the distances to perihelion and aphelion, you can figure out the velocities. Okay, they're going to be in proportion according to a conservation of angular momentum. Now, let's talk about spin angular momentum. And a good example is just like a disk here. In an old-fashioned computer, you have a disk. We call it a disk drive. It actually had a little plastic disk in there. And DVDs and Blu-rays and stuff, CDs, those actually are disks, and they spin really fast. So the angular speed is like for this one, 600 RPM. RPM, revolutions per minute, is an angular speed or an angular velocity. All right, so the spin angular momentum, it's an angular momentum. It's the sum of a bunch of orbital angular momenta. For every pixel of your disk, it's going to have MRV. And if it's a circular disk, it's going to be fairly easy to figure out MRV. But all the R's are going to be different as you go from the center of the disk to the outer part, and the V's will be different because further out, they're going to be higher speeds. So for a rigid object, they're all on the same angular frequency or angular speed, and the symbol for that is omega. So this formula angular momentum equals capital I times omega. Omega in this diagram is 600 RPM. Which you could convert that to 10 RPS, 10 revolutions per second. Okay, or just 10 per second. So now, the moment of inertia is the quantity called I, and we're going to try to figure out that. Now, moment of inertia is the rotational analog to the mass. Okay, and for the door, the point at which you apply the force, the spin rate of the door depends on where you apply the force, and also to how many kilograms of wood and steel and plastic there are at every inch away. The first inch away from the hinge, so many grams and kilograms. Second inch, third inch, 10 meters out, 10 centimeters out, or 10,000 kilometers if you're talking about something in orbit. Okay? Now, electrons are the exception. We don't know what the structure of an electron is. They seem to have intrinsic spin, angular momentum, but we've never been able to think of or measure, like, okay, if the electron is a sphere and it's got spin angular momentum like the Earth, the Earth's got, a huge number of kilograms. It's 6,371 kilometers for its radius approximately, and it spins once per day. So what would that be? RPMs. That's a pretty small RPM value, one spin per day, because there's a lot of minutes in a day. How many minutes are there in a day? 24 times 60. What's 24 times 60? 1,440? Is that what it is? 14. Okay, do 1 over 1440. So it's going to be like 0.000 something. 0.00069 RPMs for the Earth. So the Earth's got a pretty low RPM value, revolutions per minute. But anyway, so photons also have spin. We don't understand that. We know that they have spin. They obey angular momentum rules, but we don't really know what the structure of the photon is or the electron. They're very mysterious. There's still a lot of things about the universe, Don't ever think that scientists are, like, we got it all figured out, buddy, and especially don't ever think that about the engineering department. Those guys over in engineering majors, they want you to think they know everything, but we don't. We got to be humble about that kind of thing. Anyway, so let's take a look at this. So, so here's your disk spinning, and you can see omega's sketched in there. In this case, it's kind of coming around like this. All right, and every point on that rotating body has the same angular velocity omega. So if it's rigid. If it's not rigid, then you got, you can still do everything, but for a rigid object, it's pretty basic. Right? It's fairly easy to handle. All right. Now, thing is, though, 2 points at different distances from the axis, they're going to have different speeds. So stuff out here at the edge of this disk is going to be going pretty fast, a higher number of meters per second than stuff down in here close to the axis. Close to the axis, Lauren, you're going to get meters per second, but you're going to get way more out here at the rim. All right, so V is not, you can think of each layer of the disk, the first centimeter, the second centimeter, third centimeter, all the way out to the last centimeter at the rim as having the same speed. And you can do L equals MRV for each pixel and then add it up and stuff. But it's kind of tricky to do that. So, but I'm going to show you how to handle that with moment of inertia. Now, a couple things I want to point out to you, and that is There are several angular momentum videos in YouTube. Now, it's not on the playlist for lecture. But if you go up a level in the Physical Science 1121 YouTube site, you'll see, like these different, you see demonstrations, angular momentum, diffraction. Here's fall 2015. I mean, you'll see playlists from other semesters, and then this one is the one that you want to focus on. And I'll try to get the demonstrations in here on Thursday, and then on exam 2, I'll probably ask you a brain burner about the bicycle wheel demonstrations that we do on Thursday, hopefully. All right. Now, as I mentioned, where you apply the force on an extended object is important. Here's another diagram from the textbook, F1 and F2. One of them's up, F1 is applied at the center of mass. So you're pushing right through the center of mass. You're just going to accelerate straight up. But if you push at as force F2 does through point A, you're off the center of mass. That board's going to accelerate upward because you're giving it some newtons. You're giving it a little acceleration. It's also going to spin as it goes. All right, so baseballs and cannonballs and stuff, those are point objects. They're rigid, they're spherical, but a real object like a board will take a complex trajectory depending on F equals ma and also on torque effects. All right, so we're going to look at some pictures of that. So the distribution of matter and where you apply the force, as I said before, it really matters. And we're going to calculate the numerical quantity, the moment of inertia, capital I, that is the rotational analog of mass. But before we do that, I want to look at some pictures here. All right, now, a complex trajectory, that means it's translational and it's also rotational. Now, here's an example of translational motion, crescent wrench. And this is obviously a metric crescent wrench. So, so this is an overhead view. You're sliding it across the table, fairly smooth table, and here's some. There's a black diamond painted on this wrench. And it's a set of strobe images of it. And I put these blue diamonds. All right, so there's where the black diamonds are. All right. And you can see that it's moving. Here's the blue diamond. It's moving straight across. The center of mass is moving straight across. But the distribution of mass, the entire wrench, is also spinning as it goes. So that's a combination trajectory. And here's another one, which, I don't know. I would not want to do that. Especially after eating at Taco Bell or something like that. You're going to lose your lunch. I mean, can you imagine how nervous that? I mean, he's probably not nervous in this picture, but the first time he did it, oh my goodness, he was probably sweating bullets. Here's another picture. This one's a little easier to see. So you see, he's got a parabolic arc there. It's nice, but he's also spinning. Can you imagine you've got to be able to spin yourself over here on the right side at the takeoff at just the right speed of spin, and he's doing a backflip. So he's spinning backwards. So here he is. He's spinning. Here he is. Here he is upside down. Right? So he's upside down right at the top of his arc. All right, so here he comes back around. And here he comes back around. And so now he's ready to land. Okay, so he took off parallel to the ramp, and he landed parallel to the ramp. So can you imagine teaching yourself that? You know, because in other words, can you imagine the first couple times he does it and he doesn't get it right? And, oh my goodness, talk about nervous. I mean, because you got to get this right. You have a little bit of plus or minus, but you don't have much. You're going to break every bone in your body. But you know that guy, that famous daredevil, Evel Knievel? And a lot of these motorcycle daredevils, they say that Evel Knievel had broken every bone in his body like 7 times over or something like that. I mean, in other words, he had a lot of practice runs, and he ran into a lot of problems. But I don't know. These guys do that. They probably get paid a lot of money for that. Anyway, so that's a complex object. Moment of inertia for a man on a motorcycle. But, look at that. I mean, if you track his center of motion is like right here, like right where the engine is. I guess that makes sense. Because the wheels are below the engine, and he is above the engine, so the engine's about the center of mass. Anyways, that's a complex task to figure that out. Here's a fairly simple one. Moment of inertia. Here's all you do. The orbital angular momentum, m times r times v. For spin angular momentum, you compute this, I, the inertia, the moment of inertia, and it's just m times r squared for each pixel of mass. Now, for the motorcyclist, he's got a lot of pixels, all right? And they each have a different r from relative to like wherever the center of mass is, the engine, somewhere in the engine it looked like. Okay? Now, for these barbells, it's fairly easy, and you just figure out how far away from your spin axis. So like this one, the distance is 45 centimeters left to right, and this one a little bit bigger, 60. So this one the R would be 30 centimeters for this one, and for this other barbell, it would be about 22.5 centimeters. So mr squared would be different, even though the two barbells have the same weight and the same mass. So you add all those up together, and then you calculate the spin angular momentum. Now we're going to do that. Let me show you how to do that. Okay, so write down I equals capital sigma means the sum of, and then the little subscript pixels, it means the sum of mr squared for each of the pixels in the object that you are studying. All right, so for the motorcyclist on a motorcycle, a lot of pixels, and you got to do it right. Barbell, not so difficult. Okay, and you measure the distance from the axis. So if this is your spin axis, every pixel of iron on the left matches a pixel of iron on the right, so it's fairly easy. All right. Now let's do a calculation, a very simple moment of inertia. And you're going to do a calculation here in a minute, so and we're just going to go step by step. We'll just work it together, 50-50. All right. So let's say that you have a pair of weights. You're in the weight room. 7 kilograms, and let's say that it's 4.2, it's pretty long, it's 12, 13 feet. All right, so this is kind of an imaginary weight room. Anyway, so you got 7 kilograms left and right, and you got a 4.20 center to center distance, and let's ignore the mass of the bar. All right, that's a typical physics department lazy man technique. Forget about the bar. Let's focus on the 2-point masses, 7 and 7. All right? Draw in your axis. So let's make our axis right down the middle. Nice and symmetric. Now you can do the moment of inertia about an axis through one of the masses, if you want. You can do the moment of inertia through an axis, in Miami, 200 miles away if you want. Then it's, you got a lot of big R's and stuff. But this is the normal axis. Okay, so you got 2.10 left and 2.10 meters right. Now here's our formula. In moment of inertia, the sum over the two masses. So we just have two things to calculate together. mr squared for the one on the left, mr squared for the one on the right. Calculate them and then add them up. That's what this formula tells us. Right? So here's how it looks. Instead of this fancy compact formula with a capital sigma, how about that? 7 kilograms times r squared. This is, and this is 2.10 meters is r, and then you got to square it. So we're not done yet. We got to square that baby. And if you don't have your calculator out, better grab it and just re-verify on this. And then 7 kilograms times 2.10 meters, that's for this baby on the right. You got, this one's symmetric. It's fairly simple. I set it up to be simple. It's just a rigid rotator like this. We neglect the weight of the bar. And we just calculate this. Now here's the next level. I'll leave the 7 kilogram alone for a minute. And multiply 2.10 meters quantity squared. Anybody verify me on that? 4.41? Okay. All right, get your calculators out and verify. So 7 times 4.41, and you got two of them. They're both the same. All right, anybody verify me on 7 times 4.41? I got 30.87. Okay, good. All right. That's good because 7 times 4 would be 28, so this is a little bit bigger than that because it's not 4, it's 4.41. So, and it ends in a 7, so that's good. All right, so 30.87. And notice the units, kilogram meter squared. Yeah, that's the units of moment of inertia. And now you just got to add them up. 61.74 kilogram meters squared. And that is the moment of inertia. So the torque, or the angular speed times this, so your RPMs times this gives you the spin angular momentum for this barbell. It's an imaginary barbell, okay? So if it's spinning around this axis, the vertical, the symmetry axis, at some RPM level, like 2 RPMs or something like that, you multiply 2 RPMs times this 61.74, and you get the angular momentum. Now let's do a calculation together, okay? So hit your, actually you don't have to hit the refresh key because this is multiple choice coming up. All right, let me get the question. Here we go. All right, similar, different distances, different masses. Calculate the total moment of inertia about this axis. So, same type of axis, right down the symmetry line. Let's see what we got here. Just do mr squared for each blue mass, and that'll be good. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Good. Yeah, most of you guys got it right. The answer is 9.8 kilogram meters squared. All right. And so here's the, if you feel like writing down the calculation. A few of you got tripped up. Here's all you got to do, 2 pixels. So you have 2.5 kilograms for M, and then 1.4 meters quantity squared, and then you have 2 of them. Okay, and so 1.4 meters quantity squared is 1.96 square meters. Multiply those 2 together and add them up, and you get 9.8. Okay, now here's what I want you to think of. This quantity, the moment of inertia, it encodes the resistance to changing the spin rate. All right, so for instance, a male ice skater and a female ice skater at the Olympics, they have different masses. They have different, the male's probably going to be a little bit bigger by an inch or 2 tall, maybe a little bit wider shoulders and stuff. And, so their moment of inertia is going to be a little bit different. All right, so it might be easier. It might actually be easier for the male to spin up to a certain speed, or it might be easier. You just have to, check. It might be easier for the female skater to spin up to a certain speed, or to slow down. So it's similar to inertial mass in regard to translational accelerations and stuff. But now this is for spinning. Okay. Now, I want to point out to you that you can do this calculation for more complex shapes. All right? And there's a table, I believe, in the ebooks in Great River. Did you guys see this table of shapes in there? Raise your hand if you saw this in the website. Oh, it's supposed to be in the website. I'll have to put it up in web courses. It's a table of moment of inertia for a few shapes. Okay, so for instance, the thin hoop. All right, so the thin hoop spinning about its own central axis. Okay, so you can see that going right through the middle here. Okay, this thin hoop. The moment of inertia is just the mass of the hoop times r squared, because all the mass is out there at the radius. It's a circular hoop, okay, and it's thin, so there's no near and far. They're all the same radius, the same distance r out there. So the moment of inertia is just how many kilograms you got, and then the square of the distance to each of them. Okay, so the sum of mr squared adds up to the sum of the hoop masses times the same r squared for each part of the hoop. All Right now, down here for a solid cylinder, completely different. Now, it still has an mr squared in it. Go ahead and write this one down. The mass of the cylinder times r squared, the radius of the cylinder, and a factor of 1/2 out in front. And that, my wonderful student, encodes the significantly different distribution of mass. You know, a hoop is cylindrical. I mean, you can think of it as cylindrical. You know, it's definitely circular, and it's probably got a few inches of, depth to it. And this cylinder is not just cylindrical, but it's solid all the way through. So if it's the same density all the way through, this is the moment of inertia about the cylinder, its natural rolling axis. All right? 1/2 mr squared. So that 1/2, believe it or not, there's a ton of calculus in that. And it's not cinchy calculus. It's very tricky calculus. All right? But it boils down to a factor of 1/2. It's kind of cool. All the r squareds, the square of the radius and the total mass come out with a factor of 1/2. That's it. It's kind of cool. So the mass of the object and its dimension are usually, if it's a fairly simple object like a cylinder, that's all you really need. But you got to do all the calculus and stuff, and you get a factor of 1/2. Now, you don't have to worry about the calculus. That's why you have a table. Okay? But you definitely write it down. I equals 1/2 mr squared. Sphere. Ding. Slightly different factor out in front of it. Okay, we got the mass of the sphere, m. We got r squared, the radius of the sphere. But it's different again. Sphere and a cylinder are definitely different. And all the geometry and trig and calculus strains out all the way to the end as a factor of 2/5. That's it. That encodes the fact that you're not a hoop. The 1/2. You have 2/5 of whatever a hoop has. The sphere doesn't have as much moment of inertia. And why is that? Why doesn't a sphere have as much moment of inertia as the hoop? Why does the hoop have so much? I mean, it's got 1 mr squared. And the sphere only has 2/5 of an mr squared. And the cylinder has 1/2 of an mr squared. Why is that? Raise your hand if you want to try to explain why that is. What do you think? Yeah, call it.
Is it because it's more dense?
No, if we're saying the same density and the same mass, if we say that each of these objects is uniform density, and so the same mass sphere, same mass cylinder, same mass hoop, you have mr squared for the hoop, 1/2 mr squared for the cylinder, 2/5 mr squared for the sphere. So why do you think that is? Yeah. Correct. What's different? It's the distribution of matter. That's correct. Now, what's different about the distribution of matter for the sphere compared to the hoop?
It's more condensed. It's not going to be as outstretched.
More condensed, not as outstretched. Okay. That's like saying all the mass is way out there for the hoop. But there's a lot down towards the axis for the cylinder and the sphere. Sound good? Yeah, okay. All right, that's the reason for it. Now, let's take a look at this stick. Oh, my goodness. The stick, 1/12. That encodes the stick's moment of inertia about that axis perpendicular to the stick and through its center of mass. See, the rotational axes for the hoop, the cylinder, and the sphere go through the center of mass and are the natural roll, and they're symmetric. Same thing here. Although, you know what you could do for a stick, compute the moment of inertia along the stick axis. And that would be a little different. But for the axis perpendicular to the stick, yep, 1/12 m times L squared. So if you think of the L as being the dimension of the stick, then you get that factor of 1/12 out there. So all those factors, 2/5, 1/2, 1/12, and you can do this for stuff, it's fairly easy to do with a little bit of calculus. Well, I shouldn't say it's easy to do, but you can do it with calculus for simple objects like a cube, an equilateral pyramid, 60-degree triangles for each of the four sides of a pyramid, etc. Or like a dodecahedron, or a diamond, And every diamond, every cube, you have a different axis. You could do the cube perpendicular to each side of the cube, or you could do corner to corner. That would be a different result. You might not have the same fraction out in front. You still have an mr squared or an ml squared for a cube, but you wouldn't have the same factor if you use different axes. And all of it traces back to this example. All right? So make sure you are ready to do that next Tuesday. And if you feel like getting an A on the test. Now, I want to go through something with you called the right-hand rule. And I have alluded to this already, because I said that the angular momentum is a vector, and it's constructed from the position and the velocity vectors. And for a circular path, the velocity and the position vector are perpendicular. But like on an elliptical path, they might be at an acute angle or an obtuse angle. But here's how you figure out the direction. You got to use trig to figure out the size for that comet. But the right-hand rule tells you the direction. All right, so here's what you do. And we're just going to practice this a little bit. Okay, you use your right hand. All right, and you curl your fingers of your right hand in the direction that it's spinning. All right, or orbiting. All right, so for like the orbit of the comet going counterclockwise. So, I need a picture of a comet, and I don't have one here. But if it's going counterclockwise, you'd curve your fingers of your right hand. Go ahead and do it. No, not like this. Parallel to the screen. Okay, so say that there's an ellipse on the screen, and it's going, and the comet's going. Yeah, good. Okay, then your thumb tells you the direction of the angular velocity and the angular momentum. Okay, so if it's going so just think of any clock. If it's going counterclockwise, I should say. Then your thumb is pointing out. But if it's going clockwise like this, then your thumb is pointing the other direction. Right? So torque is also used. The direction of the torque is also in that direction. Now, a bicycle wheel, when we get to the demonstrations on Thursday, you'll see that the right-hand rule, the right hand, let's see, if you're moving, let me think about this. You're on a bicycle. Think about a bicycle. Okay, and you're moving forward. So the wheels are going, and so here's your hand. Look at me. Everybody look at me. So here's the handlebars, right? And you're going forward, right? So your wheels are going like this, right? So that means your fingertips would go like this in the direction of spin. And so the angular momentum of the bicycle wheels, if you're going straight ahead, is to the left. Is that right? Is that what? Who's got a skateboard? Anybody got a skateboard? Angelica, hold your skateboard up. Thank you. All right, so if you go forward, yeah, those wheels are going to go like this. So it's going to be, so the angular momentum is going to be to the left for a bicycle, if you're going straight forward. If you're back, well, you can't back up very good on a bicycle. But if you were, it'd be the other direction. All right, now let's take a look at the Orlando Eye. All right. So just go ahead and make a note. Dr. B's blabbing his big mouth about the Orlando Eye. All right, so I've got to go down there and try it. All right, so supposedly it spins clockwise if you view from the west and you're looking east. So this is from the west looking back towards, Brevard County, I guess. And you're looking across Orlando into, towards Port Canaveral and stuff, Cocoa Beach and stuff. All right, so it spins clockwise. All right, so that means your fingers are going like this, and the angular momentum arrow would be, and the angular velocity arrow would be into the page. All right, now go ahead and make a note of this. Into the page or into the screen, you symbolize with a circle with the letter X in it. And the X is supposed to represent the arrows, the feathers at the end of an arrow that's moving away from you. Okay, so an arrow with feathers, last thing you see are or an arrow with feathers, last thing you see as it moves away from you are the feathers. Okay, so that's what the X means. All right, so for this one, okay, it's going into so the arrow's flying into the board, it's flying to the east. So, and you're on the west side, so that means the last thing you see are the feathers. All right, so put an X. So normally the place you put the vector or the symbol for the vector is at the center of the motion, at the axle or the axis of spin. All right, so this thing is a big monster, Ferris wheel. And now let's try and look at the other side. Now let's say that you're on the other side of the Orlando Eye. So here's some guy back here. All right. Now he's in back. Okay, that's I don't know who that is. Some guy. All right. I don't even know what he's doing. What is he looking at? The plants? It must be the gardener. All right. At any rate, the angular velocity arrow is it's pointed towards Cocoa Beach. Okay? Now he's going to see it going like this. He's going to see it going, he's on the other side, he's on the east side, and so he's looking at it, it's going, for him, it's going counterclockwise. All right? So here's how it would look. All right? Except that you would put the arrow up there by the hub. All right, so here's a little diagram. It might kind of little diagram. So here's the Orlando Eye. Here's a couple of little compartments. And there's the angular. It's pointing towards Cocoa Beach. All right, and and there's the diagram. There is a diagram. So if you go on the internet and you look up right-hand rule and then angular velocity or angular momentum, you'll see a bunch of diagrams and stuff. It's kind of tricky, and I'll be giving you guys some practice with this in homework, and we'll do some right-hand rule practice on Thursday. Now, we're going to dismiss, but before we Don't move yet. We're going to have, you've got mini review for chapter 4. I activated that today. And I know some of you have done mini review for chapter 3. I'm going to activate mini review for chapter 5 Thursday. So you have between Thursday and Tuesday to do it. So get started on those mini reviews. Also, I'm going to give you homework 11 in web courses tonight, due on Thursday morning, first thing. All right? And it'll just be a couple cinchy problems for you. And then more over the weekend. Okay, you're dismissed. I'll see you on Thursday.